In the last video, we saw a 2 by 2 matrix A that was similar to another 2 by 2 matrix A prime that happened to be diagonal. And the reason that that happened was because A had two linearly independent eigenvectors called an eigenbasis. So we're going to define diagonalizability, and then we're going to do a couple of more examples. So the definition is this: an n by n matrix is called diagonalizable if it's similar to a diagonal matrix. So for example, the matrix that we saw in the previous video was similar to a diagonal matrix, so that was a diagonalizable matrix. Now, we saw that the matrix A had two linearly independent eigenvectors. It had an eigenbasis. And so Theorem 7.5 says that's all we need to know whether a matrix is diagonalizable. So it says an n by n matrix is diagonalizable if and only if it has an eigenbasis. So this is an if and only if theorem, which means that if you know the matrix has an eigenbasis, then you know it's diagonalizable. It's similar to a diagonal matrix. But also, if it doesn't have an eigenbasis, then you know there's no way it could be similar to a diagonal matrix. It can't be diagonalizable. So the proof of this theorem is in the textbook, and it's what we call a constructive proof. In mathematics, we call a proof constructive if it not only shows that something exists, but it shows how to get it. It gives us a recipe for building it. So in that proof, it shows that if the matrix A has an eigenbasis, then it shows how to find the invertible matrix P such that P inverse AP is diagonal. We're going to use that recipe. And so what it says is that the proof tells us that if A is diagonalizable, then P inverse AP is diagonal, and the matrix P consists of the eigenvectors of A. So the columns of P are just the eigenvectors of A, and the diagonal entries of P inverse AP are the corresponding eigenvalues of A, and they have to be in the same order. So the columns of P are x1, x2, up to xn, the eigenvectors. Then the diagonal entries of P inverse AP are lambda 1, lambda 2, down to lambda n. All right, let's see how to use this. So let's look at this matrix, a 3 by 3 matrix A, and it says find an invertible matrix P such that P inverse AP is diagonal. Well, it's only possible to find such a matrix P if A has an eigenbasis. In other words, A has to have three linearly independent eigenvectors. So let's see if we can find them. So the first step, of course, is to find the eigenvalues. Let's call those lambda 1, lambda 2, and lambda 3. And then we'll find, hopefully, three linearly independent eigenvectors. Let's call those P1, P2, and P3. Those are the eigenvectors. And then we'll line those up as the columns of the matrix P that we're looking for. And because those eigenvectors are linearly independent, we know P is an invertible matrix. And then the diagonal matrix P inverse AP will just be the diagonal matrix that has lambda 1, lambda 2, and lambda 3 on the diagonal. All right, so let's do step 1. To find the eigenvalues, we got to find the determinant of lambda times I3 minus A. So lambda times I3 minus A is going to be lambda minus 3, then negative 2, negative 1, then 0, lambda, negative 2, 0, -2, and lambda. And now finding the determinant is easy because we can go down that first column because it has 2 zeros in the first column. So the determinant is going to be lambda minus 3 times the determinant of the 2 by 2, lambda squared minus 4. And then if we factor it completely, it's lambda minus 3 times lambda minus 2 times lambda plus 2. And we get 3 distinct eigenvalues. That's good because we know we're going to get 3 linearly independent eigenvectors. So let's see what those eigenvectors are. So that's step 2. We're going to find the eigenvectors that correspond to the 3 eigenvalues. Lambda 1 equals 3, lambda 2 equals 2, and lambda 3 equals -2. And remember how we do that. In each case, we're going to find lambda times I3 minus A, that 3 by 3 matrix, which is going to be lambda minus 3, -2, -1, 0, lambda, -2, 0, -2, lambda. In each case, we're just going to replace the lambda with whatever our eigenvalue is. So the first one, the eigenvalue is 3. So 3 times I3 minus A is the matrix 3 minus 3, which is 0, and then -2, -1, 0, 3, -2, 0, -2, and then 3. And then we just get the reduced row echelon form. Using Gauss-Jordan elimination or technology, we get 0, 1, 0, 0, 0, 1, and then a row of zeros. Remember, we're looking for the null space of this 3 by 3 matrix, 3I3 minus A. So using the top row, we get x2 equals 0. The second row, we get x3 equals 0. And that means that x1 is our free variable. So we get the eigenvector, P1, which is just 1, 0, 0. All right, doing the same thing for lambda 2 equals 2. The matrix 2I3 minus A looks like this. It's 2 minus 3, which is -1, -2, -1. And then 0, 2, -2. And then the last row is 0, -2, 2. And then using Gauss-Jordan elimination or technology, the reduced row echelon form for this one is 1, 0, 3, 0, 1, -1, and then a row of zeros. So the top row says x1 is equal to -x3. Second row says x2 is equal to x3. And it turns out x3 is our free variable. So the eigenvector, which we'll call P2, is -3, 1, 1. So for the last eigenvector, we'll find the null space of the matrix -2I3 minus A. And that matrix is -2 minus 3, which is -5, -2, -1, 0, -2, -2, 0, -2, -2. And then the reduced row echelon form for this one is 1, 0, -1/5, 0, 1, 1, and then a row of zeros. So the first row gives us x1 is 1/5 x3. The second row gives us x2 is -x3, and then x3 is our free variable. And so our eigenvector P3 is, I'm going to use, I don't like fractions, so I'm going to use 5 for my parameter for x3. So I get 1, -5, +5 as my eigenvector. All right, so step 3, we're just going to line these vectors up as the columns of the matrix P. So the columns are the eigenvectors P1, P2, P3. So it's 1, 0, 0, -3, 1, 1, 1, -5, 5. So that's the matrix P. It's invertible because the columns are linearly independent. Those were the linearly independent eigenvectors. And then the diagonal matrix P inverse AP is the 3 by 3 diagonal matrix that just has lambda 1, lambda 2, and lambda 3 on its diagonal. I didn't even have to find the inverse of the matrix P, because we know what P inverse AP looks like. All right, in this example, we're given a 3 by 3 matrix A, and we're asked to show that it's not diagonalizable. So using Theorem 7.5, all we have to do is show that A does not have an eigenbasis. That means that A does not have 3 linearly independent eigenvectors. So we're going to first find the eigenvalues and then look for eigenvectors and see if we have 3 linearly independent ones. Well, A, first of all, is a lower triangular matrix, so the eigenvalues are sitting right on the diagonal. So the eigenvalues are lambda 1 equals 2 and lambda 2 equals 4. And lambda 2 has multiplicity 2. So we know that lambda 1 is going to have 1 eigenvector. And we know that lambda 2 is going to have either 1 or 2 eigenvectors. So we want to show the matrix is not diagonalizable. So let's just check lambda 2 and see if lambda 2 only has 1 eigenvector, then that means we don't have 3, a total of 3 eigenvectors. So let's just check lambda 2. So 4 times I3 minus A is the matrix 2, 0, 0, negative 4, 0, 0, 0, negative 4, 0. And when we get it into reduced row echelon form, it is 1, 0, 0, 0, 1, 0, 0, 0, 0. So x1 is 0, x2 is 0, and x3 is our free variable. So it really only has one parameter, so it only has one eigenvector. The eigenvector is 0, 0, 1. So A does not have 3 eigenvectors, so it does not have an eigenbasis. And that means by Theorem 7.5, it's not diagonalizable. All right, so that's how to use the definition of diagonalizability and Theorem 7.5. And in the next video, we're going to look at general vector spaces or abstract vector spaces. And I'll see you there.